Thank you.
Hello, my name is Aditi Bhattamishra, and I'd like you to join me today as I introduce the PAU, a revolution in modern prosthetics. To understand the potential of the PAU, we must first cover the pressing issues in modern powered prosthetic technology. In 2017, 57.7 million people suffered from some sort of limb loss, and that number has only grown. Despite this, there is an overall severe lack of accessibility, fueled by two key issues: uber high costs and high power consumption. You see the numbers on screen. Families looking for high-end, robust prosthetics must be prepared to spend a fortune on the prosthetic alone, with countless more spent on maintenance and doctor visits. The real kicker is when all this money is spent on a device whose battery duration only averages about 4 hours a day. Imagine that, 30K USD for 4 hours of walking normally. I would not pay for that personally. These two factors are huge deterrents for amputees, which leads to a significant decrease in quality of life. Here's where the PAU comes in. The PAU turns conventional joint actuation on its head entirely by employing a smart fluidic servo actuator, or SFSA, which uses an external gear pump to drive two cylinders that move opposite to each other. The piston motion is used to rotate a pulley, which directly acts as the ankle. By using fluidic power, the actuator bypasses the large, power-hungry motors used typically, but still utilizes the precise control motors allow for. Despite using fluids, there is no exposed ceiling, no outside reservoir, and no tubing. Everything is contained in the design's housing, and the fluid is simply circulated between two chambers. This makes the design streamlined and lightweight. Joint position is controlled by a custom-made closed-loop PID position controller with a less than 35 millisecond response time and less than 0.5 degree position error, allowing for minute changes in position instantaneously. The motor in the PAU runs at higher speeds but lower torque, which means less overall current draw from the battery. The PAU's design is also incredibly 3D printer friendly, severely lowering costs and simultaneously allowing for easy scalability. The PAU grows with you hassle-free, which is perfect for pediatrics. The specialty of the SFSA is the ability to provide a complete prosthetic through integration of human sensing for environment adaptability. This gives users the freedom to walk wherever they want with whatever shoes they want, a freedom that we usually take for granted. Here we can see a comparison of the PAU with a standardized prosthetic developed by U Michigan, as well as an actual human ankle. This comparison clearly proves the PAU is competitive with industry standards in numerous aspects, with the potential to exceed them as well. Just look at the price difference. And PAU is able to meet and exceed the torque requirements of human ankles as well. And the current prototype speed is 55 degrees per second with a closed loop control. The goal speed
30
is
seconds.
60 degrees. Now, who is affected? The PAU's impact scope is small but absolute. Innovation in this sector guarantees affecting every possible consumer of the technology because the need for better options is constant but unadjusted. The PAU is able to present a very real and very worthwhile opportunity for researchers and users alike, and has the potential to completely revolutionize prosthetic technology, commercial and otherwise, as we know it. My name is Aditi, and thank you for your time.
Good timing. All right, we can start with our judge.
Yeah, Aditi, I have followed your project. I know that you have been working on it like for about 3 years now. It's shaping great. I am actually like, and honestly, I'm really interested in your SFSA approach. The antagonistic cylinder is a brilliant idea. My question here is, have you done like more testing? Have you determined the torque and operation parameters? Like, so is it capable of withstanding the necessary mechanical stress for walking?
So I haven't done clinical testing, so I haven't actually put it on someone who is an amputee because that's a whole different ballgame. But I have done like stall tests for the actual toe measuring torque from this point, and it is able to be. And so the requirement for the ankle joint is 47 Newton meters. It's able to go above that easily.
Great, sounds great. Thank you.
Thank you, Aditi. That was a wonderful presentation. But again, it was, to be honest, it was a little out of my league. I don't quite understand the well, I understand the theory behind it, but as far as the
I'll walk you through
it, it's a little out of my. But there's two things that really do interest me. One is that when do you think you could have some trials out on people like amputees? When do you think that would likely take
I've
place?
been reaching out to local hospitals. It's a difficult process because you have to find someone with the type of amputation that I can test this on. You have to be willing, stuff like that. The hospitals have to be willing. So I'm currently in the process of reaching out. There's more refinement I'm doing from my end as well. So this is constantly evolving. But yeah, that's definitely in the plans for the future.
Oh, well, if you ever thought, like, if I was an amputee, have you ever thought of just like advertising in a newspaper, or just advertising for people not going through the medical system? Because I know if I was an amputee, I'd go, wow, I would kind of be willing to give this a shot or to try it out. Have you ever thought about that, or is that a feasibility?
Well, so because of the way things when it comes to medicine work, typical forms of advertising isn't usually as easy to do because there's issues with like confidentiality and whatnot. And also,
Yeah, I get you.
it's easier to sort through resources if you first contact a health professional and then have them recommend patients, as opposed to reaching out to patients themselves, because health professionals will also tell you where to find the equipment to measure the things I need to look for. So a lot of prosthetic testing in general requires a lot of specialized equipment that's not readily available. I've had to kind of do it, DIY it very, very vaguely in my basement.
Yeah.
Yeah. So
I absolutely understand. And just a quick question. Sorry, Susie, if I'm taking your time, but why does it interest you? Why do what you do?
I actually, wait, I want to share my screen again. Never mind. I closed the presentation. But on my first slide, I wrote "Make Science Fiction Real," and the story behind that is when I was in 7th grade, I watched a TV show. It was like a reboot of a very popular kids show called Voltron. You may have heard of it. And there was a character there who had this really cool prosthetic arm. And my mind at that moment was like, why don't we, like, what's preventing us from reaching that like standard? And that kind of led to a rabbit hole of Googling,
minute.
and then yeah.
Wow, thank you. Wow, thank you.
Mhm.
Oh, yours, Susie.
Thank you. Great job. I love the fact that you have this path of, the next step that needs to happen and the next step. And but I do have a question for you.
Mhm.
Because of the hydraulic component to this, can you envision someone using this to run versus just walk?
No, well, okay. So when it comes to daily use prosthetics, those are the ones that are usually mechanized. So there's motors involved in those ones. You're not meant to like full on sprint in those, period, because it's not worth it to use so much power to power this when you're running, because there's a lot. When it comes to athletes, you'll see like Paralympics, like sprinters and whatnot.
I've
They
seen
have
that.
like the hooked ones. Those are a lot better because they're lighter, and they're better for sprinting because they give a lot more return energy, which is not something you're concerned about when it comes to daily use. So it's a whole different type of movement that is not suited for powered prosthetics, period.
And we're going to have to wrap it up right there.
Okay. Thank you.
Great
Good
job,
job.
Aditi.
Thank you.